Hello, welcome to the second lecture of this course on modeling, analysis and estimation of three-phase unbalanced power network. In the last lecture, we have talked about the inductance of a cylindrical conductor of finite length, and from there on we will be now be continuing. So, the last lecture we talked about the inductance of the or rather the impedance we talked about impedance of a cylindrical wire of finite length, of finite length, that we have talked, and that expression we have said that z is equal to r plus j omega k into log twice s plus ds minus 1. That is what we have talked about. So, z is the impedance. So, this is the impedance, this is the resistance, this omega is the frequency in radian 2 pi f 2, 2 pi f. K is a constant, we have said that it is 2 into 10 to the power minus 7, and S is the length of the conductor. Please note this is Henry, so this is would be ohm per meter, because everything is, because that inductance expression was Henry per meter, it was per unit length, and R is the radius. So, that is what we have looked into. Now, with this, what we now consider a very fundamental concept which is called Carson's line. So, what is a Carson's line? Essentially, what we have is that I have a conductor point A to A dash, and it is carrying a current I A. Now, obviously, for actually completing the circuit, this current has to come back to the source through ground. Now, what happens that when this current is actually coming back to the source through the ground, in the ground it actually encounters many multiple paths, and then the current is actually gets split in the ground through all these multiple paths, and then ultimately actually goes to the source. Now, long back, almost 100 years back, it has been shown that the effect of all those multiple lines can be thought of by an equivalent conductor below the ground with some impedance. Let us say this is D, this is D dash with some impedance. So, let us say it has got ZAA and it has got some ZDD with some impedance, and here what is happening is that here I do have an local ground, and I do have an remote ground. So, this is the remote ground, and this is the local ground, and then this is connected here, and this is also connected here, and this is connected here, and this point is VA, and the distance between these two is DAD. Now, how this distance DAD would be computed? This distance DAD would be adjusted such that the measured value of inductance of this entire system, or rather basically the measured value of the inductance of this conductor AA dash would be equal to the calculated value of the inductance. And of course, here it is ZAD, the mutual impedance between the conductor AA dash and ZDD. So, this is ZAA. Now, this one we actually called, it is called the primitive impedance. Primitive impedance of the line. So, this Z by bar, we are simply saying that it is the primitive impedance of the line. So, then therefore, this particular original line AA dash has gotten primitive impedance ZAA, Z dash AA, and then I do have another fictitious line DD dash which has gotten primitive impedance ZDD, and then I do have another, and then what I do have? I do have also the mutual impedance between the original line and the fictitious conductor, which is given by ZAD dash. And of course, the depth of this conductor DD dash from the original conductor is given by DAD, and this value DAD would be adjusted such that the measured value of the inductance of this line AA dash would be equal to the calculated value of the inductance considering this particular arrangement, right. So, now what happens? So, now we know that from this I can say that with this arrangement. So, now if this current is IA, so then obviously this current is coming back here IA. So, then with this I can say that my VA minus VA dash would be is equal to ZAA IA and then minus ZAD IA, because this is the mutual impedance ZAD multiplied by the current IA, but then here now the current is going opposite to that original direction. So, then therefore, it would be minus IA, right. Similarly, VD minus VD dash would be is equal to ZAD IA. This part is due to the mutual impedance between the original conductor and the fictitious conductor minus ZDD, that is the self impedance, self primitive impedance ZDD into IA. It is actually basically ZAD into minus IA. So, then therefore, it becomes ZDD into IA. So, then therefore, if I take these two equations together, I get VA minus VA dash VD minus VD dash in matrix form ZAA minus ZAD, then ZAD, no, ZAD and ZDD we do not take this minus here, IA minus IA. So, this would be the matrix representation of these two equations. Now, what is the expression of ZAA? It would be, let us say, RA plus j omega k into log twice s by dsa minus 1, right. DSA is nothing but 0.7789 into radius of the original conductor AA dash. So, I repeat that RA is nothing but RA is the resistance of the conductor, original conductor AA dash. Please note that the resistance is the original conductor, it is the original conductor, and S is the length of the conductor, and DSA is actually 0.7789 into RA, and RA is the radius of the conductor AA dash, right. Now, what would be ZDD? ZDD would be RD plus j omega k, length is same. So, then therefore, log twice s by dsd minus 1, right. We will talk about this dsd little later, and Rd is nothing but the radius, Rd is nothing but the resistance of the fictitious conductor d dash, right. So, this is the resistance of this fictitious conductor d dash, and then what would be Z AD. So, this is just due to the mutual inductance. So, then obviously, it will have no resistive component. So, then therefore, it will be j omega k log twice S divided by the distance between these two fictitious conductor. So, it would be d a d minus 1, right. Now, what happens is that, now look at this diagram. This point we do ground. So, then therefore, I can say that Vd is equal to 0, and also we have put this conductor at such a point such that the potential of Va dash and the Vd dash are to be equal. Basically, this particular conductor is put at such a length such that to ensure that the potential of Va dash and Vd dash, they are equal. So, then therefore, I can say that Va dash minus Vd dash also equal to 0. Please note that this is a fictitious conductor. So, we are adjusting its distance, and then we are also assuming that this fictitious conductor is such that its potential at point d dash would be exactly equal to the potential of the point at V dash. So, then therefore, with these assumptions we can say that my Vd is equal to 0, and V A dash minus V D dash also is equal to 0. So, then therefore, with this what I can say now, from these two equations I can write down that V A minus V A dash V A dash minus V D minus V D dash would be equal to V A minus V dash is Z A A I A minus Z D A D I D. So, Z A A I A minus Z A D into I A minus this V D minus V D dash is Z A D I A minus Z D D I A. So, it is Z A D minus Z D D I A, right. So, then therefore, I can write down this equation that V A minus V D minus V A dash plus V D dash is equal to Z A A I A minus Z A D I A minus Z A D I A plus Z D D I A. Now, we have already said, now this quantity I can also write down. Now, this quantity minus V A dash plus V D dash, as I can also write down as right. I can also write it down that. Now, we have already said that this quantity is 0, this quantity is 0. So, then therefore, it only remains that V A is equal to, if I take I A common here, Z A A minus twice Z A D plus Z D D into I A, right. So, this also can be written as Z A A plus Z D D minus twice Z A D into I A. So, you see, now this is a relation between only V A and I A. So, this I can say that this is the impedance Z A A. Please note, here I am not giving an bar, because this bar we always use to denote the primitive impedance, right, but here we are not denoting the bar. So, then therefore, the impedance Z A A is given by Z A A, that is the primitive impedance, plus Z D D minus 2 Z A D. So, this is the self impedance of the impedance of the conductor, right. So, this is the impedance of the conductor. So, now let us see that with these expressions, now if I now put these expressions into these, now if I now put this expression and this expression into this, let us see what we do get. So, now what we do get is that Z A A is equal to Z A A plus Z D D minus twice Z A D, right. Z A A is given by R A plus j omega k log twice S by dSA minus 1. Please note that this is the expression of ZA, RA plus j omega A into log twice S by dSA minus 1, and then ZDD is RD plus j omega K into log twice S by DSD minus 1. So, you also put that RD plus j omega K log twice S by DSD minus 1, right, and then minus 2ZAD. Now, what is the expression of ZAD? ZAD is j omega K log 2S by DAD minus 1. So, it would be minus j 2 omega K into log 2S by DAD minus 1, right. So, then therefore, what do I get here? I get RA plus j omega K into log twice S by DSA minus j omega K from this, expanding this. Then I expand this RD plus j omega K into log twice S by DSD, then minus j omega K, expanding this. Then what do I get? Minus 2 j 2 omega K into log twice S by DAD, and then minus minus plus plus j 2 omega K. That is what we get. Now, you see this minus j omega K and this minus j omega K and this plus j 2 omega K, that get cancels out. So, then what we are left with? We are left with R A plus j omega K log twice S by DSA plus RD plus j omega K log twice S by DSD, and then minus j 2 omega K log twice S by DAD. That is what we are left with. Now, what I can write it here, we can also simplify this as RA plus RD. So, we take the real part because all are imaginary part, and now we take common. We now, if I take common j omega K, then what do I get? I get log twice S by DSA plus log twice S by DSD minus 2 log twice S by DAD. That is what we get. Now, you see, we know that log A plus log B is equal to log A into B. So, then therefore, that I can say that RA plus RD is plus j omega K into log of twice S into DSA into twice S by DSD, right. This plus this is equal to log of this into this, that is the standard logarithm formula, and minus, now twice log of something is nothing but log into that square. So, then therefore, it would be log twice S by DAD square, correct. Now, what happens? Now, we know we are basically using that log A plus log B is equal to log AB, these are the expressions we are using, and log twice log A is equal to log A square, that is what the, in case it is not clear. And then we also know that log A minus log B is equal to log A by B. So, we would be using these three, we have already used this two, now we would be using this. So, then therefore, from this and this what I get is R A plus R D plus j omega k log 2s into 2s is 4 square. So, it is 4 square into dsa into dsd minus log 4 square by d square, right. So, it would be R A plus R D plus j omega k into log 4 square by dsa into dsd into dad whole square by 4 square. So, this cancels out, right. So, then therefore, I am left with that ZAA is equal to, so then therefore, I am left with, ultimately I am left with that ZAA is equal to RA plus RD plus j omega k log DAD whole square by DSA into DSD. So, this is the expression of the self inductance, or rather we call it the self inductance of the conductor. So, this is the expression, the final expression of the self inductance of the conductor, right. So, this is the impedance of the conductor. Please note, impedance of the conductor, impedance of the conductor, impedance of the conductor of finite length in the presence of ground. So, it is the impedance of the conductor of the finite length in the presence of ground. So, you see, because why it is ground? Because you see in this we have actually considered two ground, because at point A and point A dash there are two grounds, right. Because for example, if this particular transmission line is, let us say, 100 kilometer long, so then therefore, at point A there will be one local ground, and at point A dash also there will be another local ground, and then but then ultimately this conductor current is actually coming back to point A through the ground. So, then therefore, this is the impedance of the conductor involving ground. So, when we consider the presence of the ground, so that is the impedance of the conductor, and these expressions are the central of our understanding for the development of the impedance matrices for a three-phase transmission lines. So, we will look into those aspects in the future lectures. Thank you. Thank you so much for your patience. Thank you.